which the model is more sensitive, we say, you understand what's the physical meaning of a parameter. So you understand that, for instance, Cmax is effective on the peak flow, but not on the low flow, or vice versa. I'm just talking now. And this is very useful because, as I said, I mean, you have to avoid the use of a model, the uninformed use of a model. If you use a model and you have no clue of what the model is about, this is not good. If you do the trial and error calibration of a model, you learn what's the model about. But, as I said, there are downsides, and sometimes you cannot use this procedure. So what if you cannot, for many reasons? Then we have the fortune that we have a computer. And therefore, there are some, I already discussed this, there are some alternative solutions. And an alternative solution is to instruct the PC in order to find the best combination of parameters. So this is relatively easy. We give an automatic repetition, an automatic run of the model to the PC, and we can say the PC to run the model millions of times, and then to find the application, to find the combination of parameters that is best performing. And millions of times, you know, even if the model is not very fast, if we can do something else meanwhile, because we run the computer during the night, or we run the computer for 1 week, but we are continuing to work during that 1 week, this is fine. So the problem of the time length of the simulation can be easily overcome if we can automatize the procedure. And this is certainly possible because we can pick up random values of the parameters by making a random selection and tell the computer to run the simulation for each of these random values. What is the bottleneck? The bottleneck is that we have to give to the PC a criteria for deciding when the performance improves. And this is called, this criteria, objective function. The computer needs a number. Artificial intelligence is not able to make a visual assessment. Artificial intelligence needs a number. Keep in mind that this is the downside of this procedure, that you have to translate your human assessment, which by far is much better, into a numerical assessment, which is probably more objective, but not as comprehensive as a human assessment. By the way, I open and close a parenthesis. This is a debate that is extremely interesting in the selection of personnel. Because in the public sector, given that we are using public funds, we are required to use objectivity in the selection of personnel, which is perfectly fine to avoid corruption. And therefore, we are required in the public sector to select the personnel based on numerical translation of the performances of a person. This numerical translation of your CV, it's something that is certainly objective, but is not as comprehensive as a human assessment is. So in the private sector, they totally refuse to use numbers to qualify people. They want to make a human assessment. And they can do that because they don't have the problem of corruption. They are responsible for what they do. They are using their own money. And therefore, this is something that we are heavily discussing even in the university today, because in the university, they require us to translate the skills of people into numbers. And this is something that it has a proper justification given by the fact that we are using public funds and we have to avoid corruption, but on the other hand, it's sometimes really demotivating people, because you know, one works and then everything is translated into a number. It's something that really needs to be carefully taken into account. Same here. You translate the performances of a model into a number, which is more reasonable than translating the performances of a human, but still you have to support with this model your design and make sure that the translation of your design into numbers is correct, is doing a good job. So we have to find an objective function. And it's relatively easy. I mean, you know for sure what is sum of squares. So here, what can we read here? Theta is the parameter vector of whatever model. In I mod theta is a vector that includes 5 parameters. So you define a function of theta, of the parameters, which is your objective function. And there is an easy way to define it. I take the difference between observed xt, whatever value it is, okay? And here it is expressed as a function of time, but it can be also expressed as a function of space, minus the simulated by the model corresponding value, x hat t. So this is the error. It's the simulation error. You square it, and you sum all the errors. This is sum of squares. Why do we square? Because we don't want positive and negative errors to compensate each other. It's very simple. And then there is, in statistics, plenty of proofs that provide justification for this objective function. Why do we need a justification? For the very reason that I mentioned just now, just 2 minutes ago. When you select an objective function, be careful. This is a numerical translation of your model performances. Is a numerical translation of your responsibility in a design. So be careful, it's justified. In this case, it looks justified because I take the error, which is a good indicator of the model performances, and I square it because I want to avoid the compensation. But why square and not simply absolute value then? In statistics, they prove that under certain assumption, it's more consistent, it's more solid to square the error instead of taking the absolute value. So, this is a delicate step in your activity. You always use models. Remember, you are an engineer. So, okay, sometimes we can just look at observations. But if the design becomes elaborated, complex, then you use a model. And you have to be careful that the model is a good representation of the reality. Calibration, the model always includes parameters. There are some non-parametric models, but they are very, very simple, very limited for simple problems. Usually you have parameters. Calibration is an essential step. And by far this is the most used objective function. Then what you do is just ask the PC to run the model a million of times and to retain the combination of parameters that leads to the lower sum of squares. This is very simple to do. And in R, you have automatic procedures for doing that. So once that you have the code of imod in R, you can run automatic functions that are already embedded in it that do the job for you. But you have to know what is the objective function, whether the objective function is good for you. I anticipate that this objective function is fine for us for some application, not for others. And I would be curious if you thought about it, and not much, just think about it 10 minutes, and think about a river, a model that I know, for instance. And it would be very nice if we could discuss next time, based on your reflections, but as I said, 10 minutes, 15 minutes, what are the applications for which this objective function is fine, what are the applications for which it's not so good. And I tell you, if you can understand it without making any elaboration, without making any mathematical computation, just by your intuition of engineer. Try to make an effort, and next time I need to remember, we may have a discussion at the beginning, and you tell me what are your reflections on that. Okay, very good. Thank you. Sorry. The subject of this